pseudo emergency that I have, but that's already clear how. And thanks for your understanding. So before I get started, I'm actually going to say I've updated um, the Zoom link that we're going to be using for office hour, and office hour is going to be on Friday. So I just want you to take note of that. So it's going to be on Friday because this class we meet um, oh yeah, so on Friday I can meet a student from 10. I can meet on set of student at 12. So in case you need clarification on what we're doing. So before going into another material, I promised I was going to, go over this yesterday when we meet today. We have what we call two-way multivariate analysis of variance. The idea behind the two-way is the reason why it's called two-way is because you have two categorical factors. So the two categorical, and why is it called multivariate? It's called multivariate because there are so many variables. Okay, so and that's why this is going to be called multivariate two-way ANOVA. Okay, so we have assumptions underlying whatever we do in statistics. Assumption is that we expect multivariate, we expect the variable to follow multivariate normal distribution. So whether variable in factor A in the first categorical factor or variable in the second categorical factor, they all collectively going to follow multivariate. That's why you see SLKI. Okay, so this particular observation now, follow that. And if you want to talk about model, because moving forward, we actually need to specify model, to be able to, conduct statistical inference, or with that. And this is the model. So the model here is just giving you idea that you have the data can be decomposed into the overall mean and into the treatments that has to do with factor. The first factor, the treatment, has to do with the second factor, the interaction, okay, and the error. So now this is the model, and of course when you have, because a model, we always specify model in terms of parameters. All these are parameters, of this model. Okay, now if I now want to talk about the sample, how we're going to estimate each of the parameters stated in the model. So to estimate this population mean, we're going to use the sample mean, because I believe the sample mean is an unbiased estimate of that. But this population mean is a population mean vector. Why? This is also going to be a sample mean vector. Now the treatments or effects for factor 1, or maybe I'm going to say for factor K or whatever. So this is this, which means I'm going to be subtracting that from that. So and so on like that. So this is just giving us how to estimate the parameters that we have in this. Okay, so the better way to implement multivariate analysis of variance is to go by way of ANOVA table. So in the ANOVA table, you're going to have in the source, you're going to have the factor. You're only going to have factor 1 and factor 2 because that's why it's called two-way. But we're also going to have interaction, okay? Because interaction may be significant or not, but we need to first consider interaction. So what is the meaning of interaction in the actual sense? we want to test if the effect of factor 1 on the response may depend on factor 2, okay? Or factor 2 depending on factor 1. Now, this is the model, or this is the ANOVA table, okay? This is the sum of square or cross product section. All of these are going to be in matrix form. And these are their corresponding degree of freedom. Okay, now if we want to talk about what this guy is trying to say is, okay, the total sum of of variation cross product is actually going to be the addition of all of these. So here, the variation explained by the first factor, the variation explained by the second factor, the variation explained by the interaction of the factor, and the unexplained variation. Okay, now because we're going to have 3 sets of hypotheses. The first one is going to be, testing or, for factor 1. The second one is going to be testing on factor 2. Because the factor 1 has levels, factor 2 has levels. Then we're also going to test for their interaction. So what you see here now, this is the non-hypothesis. We are actually testing that the effect, alpha 1, alpha 2 up to alpha A. Where do I stop at alpha A? Because the levels of factor 1 is A. Okay, so we're testing that they're all equal to 0, which means all equal to 0. I'm trying to say, there's no significant difference, when it comes to comparing the means, Now, this is going to be the test statistic that we're going to use, which is the ratio of, all this is going to come from the moment you get the matrix, from this table. You're just going to find the determinants. So the wiki lambda here for factor A, this is a wiki lambda for factor A. And what distribution is it going to follow if I'm going to take a decision about rejecting H naught or not? Okay, so the test statistic is now going to be whatever I got here. I take the logarithm of that. I multiply by VA. What is VA? This is how to get my VA. Where A is the numbers of levels in factor 1, B is the numbers of levels in factor 2, N is the number of observation, P is the numbers of variables. Okay? And if this guy is greater than the critical score, with that critical score, that follow chi-square distribution. So where the degree of freedom is A minus 1, you're going to check that against whatever level of significance. We're going to do the same thing to factor 2 and to the interaction. Okay, so there are 3 sets of hypotheses. Now, how do we do this in R? And I need you to pay attention. How is going to save us a lot of time. Even though I wanted to know this formula, okay, I wanted to know this formula a lot, but because we're going to be working with massive data set, so it's better we use R, to actually implement, whatever, characteristics of interest we want to figure out. Now, we have data set in R that we call empty cows. Okay, you can hear me, right? Okay, that we call empty cows. Okay, we got 4 variables. 4 variables are response. These variables here, they are the outcome variables. Outcome. And that's why it is called multivariate, because you have more than one outcome variable. Okay. Now, we have 2 independent variables. Independent. Okay. The 2 independent variables, the first one is factor 1. The second one is factor 2. These are independent. These are independent variables. But those ones, MPG, the MPG, the DISP, okay, HP, and WT, all of these are the response variable. The reason why it is called multivariate is because of this. The reason why it is called two-way is because we got 2 categorical factors. Does that make sense? So factor 1 has A levels, factor 2 has B levels. Now, in this example, the two categorical factors are the cylinder and the transmission. So here we're trying to tell you out, why we put factor is because factor is categorical. Okay, just wanted to take note of that. Now, if I now want to run this in out, what is it called to run multivariate or two-way multivariate analysis of variance? I wanted to take a look at this. Okay, your x, this is your x. Okay, your variable s. Okay, the data matrix. Now you're gonna write this LMS linear module on S, then on that cylinder transmission. Now, what do you take note here? That's a multiplication, right? When you have a multiplication sign between two categorical factor, it means you are including interaction. You want to have a separate of the factor. You also want to have the interaction. Now, the result that you're going to have. And let me also tell you this. Just wanted to see another thing. What I also wanted to see is we're using weeks. Okay? Somebody can decide to say, let me use Roy, the other alternative, but I'm using weeks here. Now, this is the result that we have. In this result, this is the output. In this output, what is going to be displayed in the output is going to be the factors, you're not going to see any of the response. Does that make sense? Okay, so right now, okay, you see cylinder, you see transmission, then you're also going to see the combination, which is the interaction. So where you see the degree of freedom 2, it means you're comparing 3 cylinders. It means A equal to 3. Don't forget, the level of factor 1 is A. Here A equal to 3. And the transmission, where you say 1, it means B equal to 2. Because 2 minus 1. Okay, so in the cylinder A equal to 3, in the transmission B equal to 2. Now, what you're now going to pay attention to right now, okay, so what you're going to pay attention to is this guy here. Okay, now you want to pay attention to that. Okay, the 1 point. So you look at the p-value. So this gives a p-value if I want to take a decision about cylinder. So this is trying to say, when you look into this simultaneously, all the response, okay, when you put this into consideration, okay, the 3 cylinders level, okay, they are statistically significant. There's a statistical significant difference between them. The cylinder, I think 4-cylinder, 6-cylinder engine, and 8-cylinder engine. The same thing with transmission. These guys, how many transmission do I have? Because the degree of freedom is 1. I got 2 levels of transmission. So it means there's a statistical significant difference between the level of the transmission. But when you take a look at the interaction, the interaction between them here, actually trying to say, if I'm looking at does the effect of cylinder on this multiple response variable depend on transmission? And this now answer the question, no, because the p-value is greater than level 0.05 level of significance. Is trying to say it doesn't have, the interaction is insignificant. So which means effect of transmission or effect of cylinder on the multiple response variable is independent of transmission, and that of transmission is independent of cylinder. Now, because of this insignificant result for transmission, for the interaction, we're now going to rerun another one. We're going to rerun an additive module. I just wanted to take note of this. Now we're putting a plus. When you put in a plus between the two categorical factors, it means you do not want interaction. So right now, for cylinder, okay, so you can see your cylinder and the transmission is still significant. Is there any question for me here? Now, it doesn't end here. When the non hypothesis is rejected in ANOVA, then we need to conduct a further test. We want to know where the difference lies. Okay, but let me tell you this. I do not need multiple comparison on transmission. Can someone tell me why? For extra credit, why do you think I do not need multiple comparison for transmission, but I need multiple comparison for cylinder? Thank you so much. We only have two. So we all know that, oh, different, lie between them. So thank you. Send me a message for extra credit. So we only have two levels for transmission. We do not, if you waste, if somebody want to waste time and still do it, he's still going to see that is not insignificant. Now, because of that, and you know what we're going to do, before we conduct multiple comparison tests in analysis of variance, we need to first adjust the means. Adjusting the means is what we call the least square means. We are not going to use the raw group means because of the fact that the raw group means is going to be misleading. What are we adjusting for? We are actually adjusting for repeated measure. We are adjusting for situation, maybe if we have unbalanced design. Of course, in this case, we have, if you consider, what we're doing. Now, which is this guy. Okay, now, if I'm going to adjust, I'm actually going to adjust, okay, on, putting into consideration, I'm going to adjust for one response variable at a time. I want to know what would be the adjusted mean of this category for each response variable. I needed to pay attention. If you take a look at what I'm seeing, what I'm doing here, okay, if you take a look at this guy, that is for only MPG for the first response. I'm going to do it to all the response variable. I got 4 of them. And if I'm doing that, I'm going to do that for each factor. Now, for factor 1 now, factor 1 is cylinder. I got 3 levels of cylinder. Then I need 3 adjusted means. These are the adjusted means. Because these adjusted means are random variable, I need a standard error for each of them. Then I need to be able to create a confidence interval, because without the standard error, there is no way I will be able to quantify the uncertainty. Now I'm getting the confidence interval now. Getting the confidence interval. You know what it tells us? I'm actually going to see this. Please pay attention. Okay. What does this tell us? There's no 0 in any of the interval. Then it's telling us that the adjusted mean is reasonable. Does that make sense? Now I'm going to do the same for MPG for the other categorical factor for transmission. Okay, so the only one I show here is just for the MPG. You're going to do it for all the response variables. Does that make sense? Okay, so this is going to pave way for the multiple comparison, because you don't want to use a raw group mean that is not adjusted to do that. Okay, so you're now going to the multiple comparison now. In the multiple comparison, because I've said in this class, Bonferroni correction 1 is the one that makes sense. The Bonferroni actually is more precise than more precise than the Ottolenghi square confidence interval, even though the Bonferroni is wider compared to the classical T. But you all know the reason why classical T is more precise. Okay, the classical T is more precise, but the classical T confidence interval does not guarantee simultaneous coverage. Okay, so right now one second. So right now, um, in the multiple comparison, I'm going to do force cylinder, force. Okay, in the non-hypothesis, the other time when we conducted multivariate or two-way multivariate ANOVA test, we rejected the non-hypothesis, saying there's a statistical significant difference among the cylinder level. Right now, we're now conducting multiple comparison. Okay, this multiple comparison, we put into consideration the adjusted mean that I talked about the other time. So we're now comparing pairwise, pairwise, and when we're comparing that, this guy is the point estimate of the difference between, like here now, 4-cylinder engine and 6-cylinder engine. This is the standard error, and this is the confidence. This is what we're looking for. If you look at the first one, you're actually going to see here, right? That doesn't include 0, right? Where interval doesn't include 0, it means it is significant. That is where the difference lies. Okay. Now it's trying to tell us the difference lies between 4-cylinder and 6-cylinder for the MPG. Okay. And if you want to do that, this is for the MPG. We're also going to repeat for each of the response variable. This is for cylinder for MPG. I'm going to do cylinder for DISP, cylinder for HP, cylinder for WT. Okay. Now the difference lies because of this. The difference lies here. Okay. If you take a look at the third one, because there's a 0 in the interval, that's for negative to positive, then it means there's no difference between 6-cylinder engine and 8-cylinder engine, putting into consideration the MPG, the fuel efficiency. MPG is the fuel efficiency. Talking about car here. Now we want to, stay on the MPG, stay on that same. We want to look at the transmission effect. But you already said the other time, it is significant, right? There are 2 levels. We do not necessarily need multiple comparison tests, but if you still do multiple comparison tests, you'll see something here. Okay, so let's take a look at for the transmission. Let's go to the transmission. Let's come back to the what was it? What was the decision? Okay, based on this, the decision means there is no difference. Okay, the decision means oh, sorry, that one is interaction. Sorry. Now this decision means there's a difference, right? We all know there's a difference. Now let's come here now. But this difference here is actually talking about the whole of this is not just based on one response, but based on all the response. Even though there's a statistically significant difference here, it may still be necessary to look into multiple comparison. You can look into the multiple comparison, for each response variable, because there's possibility collectively in the multivariate, in the multivariate collectively, you're having all the responses together. So if the transmission is significant there, if you want to do multiple comparison, you still need to do multiple comparison, because the multiple comparison is not going to put all of them together. It's the multiple comparison, we look into the response one at a time. That's why we have to do it. So right now, for the MPG, the transmission, okay? So this is what we have. Okay? So for the transmission, this is significant because there's no 0 in the interval. Okay? You still need to do the same, even though we already know for the major one, but we need to investigate for individual one, because there's possibility. Maybe it's only MPG that will be significant Because for the major one to be significant, for all the response variable to be significant, it means at least one of the variable is significant. It may not be none, it may not be not necessarily all. And that's why we have to look at it one at a time. Okay. Now, coming here now in the multiple comparison. Oh, sorry. In the multiple comparison for MPG, you see what I'm talking about? For MPG, okay, it is not significant. The difference that exists in the transmission is not in the MPG. But here, here, in the ANOVA, let me go back to ANOVA. Okay. Okay, now the transmission here. The difference that exists here, we have put into consideration all the response variables. When we now want to do multiple comparison, we need to investigate in the one at a time. This is trying to tell me there's no difference. For transmission here, transmission level is not significant, put into consideration MPG. And you now need to look into transmission, put into consideration this, put into consideration this, put into consideration that. One of that, at least one of that, it will be the one that caused that significance. Go ahead. Okay, you say that again? Okay, this is what happened. For her to be significant overall, at least one is significant. If all of them, like what I'm trying to say, let me, that's a good question. I'm going to go back to something here. I just wanted to see here. Here. You know what he's telling us? He's trying to say the two transmission level are not the same, putting into consideration all the four response variables, all combined. Now, reason why we now need multiple comparison now, okay, is that what if we now want to compare two different cars with this cylinder, this transmission and the other transmission. We now want to investigate the effect of that on each response at a time. Now, to do that on each response at a time, when we do that on MPG, now, do you see this one? Where we are looking at the effect of transmission on the MPG, it is not significant. But in the overall, we are significant. So what I'm now trying to say is that we will not only look into this, we will also look into the effect of transmission on this, on this, on this. And I now said, since combined is significant, there is possibility at least you're going to see any one of these that will be significant. So what is not common is if a combined effect is significant and none of this is significant for transmission, that is very rare. So that is what I'm trying to say, is that this is not sufficient to just look into investigating transmission effect for one response variable only. We have to do it to everyone. Does that make sense? Because when it is significant generally, it doesn't mean it's going to be significant when you look into components. It's just like you're looking into the contribution of state to the United States. And if United States is significant, that doesn't mean Minnesota contribution is significant. But at least, so what is not possible I'm not going to say it's not possible. What is rare is for United States to be significant, and none of the states is insignificant. Do you understand what I mean now? And every these states, they are the one contributing to the United States. So that's exactly what I mean. But we're not going to have any assumption. We're going to test. We're going to see the result ourselves. So that's why I said, um, because in this slide, I only show for the MPG. So I'm now trying to erase the perception that, oh, maybe you're only going to do for one response. No, you're going to do for other response too. Does that make sense? No, we may not necessarily know until we investigate. What I'm giving out is just an assumption that, okay, if generally we're still using the same level of significance. No, because that's why we use Beferroni. That's why we're not using classical T. If you use classical T, the level of confidence will go down, the type 1 error will go up because you have so many comparisons. And that is what we're using is a conservative way. You understand what I mean? That's a good question. Very good one. Okay, so I'm going to go into the next material. We're starting this material. Okay, since we are in this material now, I think in this class I have 10 students. 5 are streaming online and 5 in person. And I'm going to divide you into 3 groups. And we assigned that today for projects. Okay? So you're going to work together and